Hello. Well, waiting for someone who is join, then I will start the class. Nowadays, only two or three people they have joined. So, hello. It's okay. Yes, yes, I'm audible. Okay, okay. Yeah, I know that's what's your concern. Yeah, I will try if it's possible then because the last time is that's like 6 to 7 because we are maybe after the next week. So we'll go to home. So for that, the 15 to 17 days like around. So at that time, I will change that the schedule. So now they won't allow. So that's why I'm not changing. Okay. Yeah, I will start the class because it's already for the 40 minutes went. So we'll check. In this class, we'll see slides is visible. What about slides? Okay. In this class, we'll see like that the problems that is based on particularly the tin metal and silicon that's we'll use. And then how that the tin metal generally from tin we'll see some that's probably related about radical formation, how the radical formation will be for the radical will be for and how that's it will react with the different way because we call them as radical are the much more reactive species and they give that most of the time they are the byproducts. But in some particular type of substrate that you will get selectivity of that product. But in radical, the main demerits is that it reacts in such a vigorous way that you will get very different product. That some byproduct also you will get. But some nice product that those which those product is not possible by the carbanion and carbocation and also sometimes also carbon also those product that you can get through the radical intermediate. That maybe you know about that N-butyl tin hydride and AIBN. Do you know what is AIBN? Do you know what is? That the azo-isobutyl nitrate. That's it. And benzene is a solvent. That in this particular reaction that we have, that's that the different type of functional group. So one is alkyl, and another one is the terminal alkyne. That you see, this one is terminal alkyne, and we have that's the aliphatic that we call them as a carbon and boron bonds also. Like a RX bond and also that's alkene and alkyne. And on the reaction with we have the N-butyl, the tin hydride, the in presence of azobutyl, azo-isobutyl nitrate. Generally, what is that? The work of that AIBA, that's we call generally them as a we call them as a radical initiative. Huh. But in this particular case, that the radical initiative. In this particular case, what will actually happen? What first will happen? Yeah, yeah, cyclation will happen, but that's we have you see we have four products, but which type of cyclation only will get like then first what will happen? That's whatever that the AIBN, the structure of the AIBN is like that. And Ajo, this one is Ajo thing. This one, whatever the nitrogen double bond, we call them an Ajo. And along with we have two. That's this molecule is symmetrical. That's why isobutyl. This one is isobutyl and nitrate. Because this one is nitrate, that's why we call them as azobutyl nitrate. And after that, the radicalization that if you give that heat or that the light also, that you will get this radical after that the removal of nitrogen gas. Why this step is much more favorable step? This is only because of the removal of our nitrogen gas. That's why that will get a that stabilize the radical that will be stabilized by our Cl group. That is the cyanide group that will be stabilized. And after the what will happen? That's we have the N-butyl tin hydride and this radical that it will upstart that proton and followed by that you will get a tin butyl tin that the N-tributyl radical and that radical is responsible for that the further generation of your radical. Generally, first that the N-butyl, the tin hydride and AIBN they are reacted with each other and you will get a corresponding that the tri-N-butyl, the the tin radical, and that radical species, this radical species, these are the most important the species in organic reaction. Yeah, that will create a that lot of the reacts with any kind of like carbon sp3 with halides that we call the bromides or iodide or that even also carbon sp2 that bromine mode also that it will reacts with them that it will give a corresponding that radical formation will happen. But in this particular cases, what will happen? That it will reacts with our carbon bromine bond, and you thus will get a the corresponding radical formation. After that, the bromide that will reacts with this tin triiso sorry tri tributyl tin radical that will reacts with our carbon bromine bond through homolytic cleavage, and you will get your corresponding radical intermediate. Okay. After that, this radical we call them as this one is primary radical, and this primary radical has three options like that it will directly react with this carbon, and also that it will react with this carbon also, and that it have also that this carbon and this carbon. But actually what will happen that's through to know that some about that we call them Baldwin rule. Yes. Yeah. uh, yeah, these are stable that why that's a Baldwin rule, but generally Baldwin rule is applicable most of the time for that the carbanion type of things. In that case, it is correct. But some radical cyclization, there is some exception also. Okay, but most of the that the Baldwin rule that will be followed by that the carbanion like that's if you have that the enolate in that particular cases that some other kind of cyclization will be happen in that cases that you will see yes for radical also it is possible but sometime that you will get some different product also that the value you know in this particular cases that the 5 exo tree do you know that the name nomenclature why that this nomenclature is exo and why that's tree do you know huh exo and then and tree dig and tot that trig that refers to the it will attack to the carbon sp2 center, and if it is dig then it will attack to it that the carbon sp center, and if it is dot dot then it will attack to carbon sp3 center. These are the nomenclature. Okay. This particular case is generally 5 exo trig these are favorable as compared to our 6 exo trig. That's why call them as 5 exo trig that will be favorable, and after that whatever the radical that will be formed in this cases is a after that the reaction after the after that the first single attack then what will happen then another radical that will be for here in this carbon, and you will get a because it was a tertiary radical, and that will again react with, and this radical also has the two choice that one is that the 6 endo dig also and 5 exo dig also, but that's why but 5 exo dig is much more favorable, that's why we'll get our 5 exo dig. We'll see that's fast this cyclation this one will be for this one this carbon and this one will be for after that this carbon and this one will be for why that this one whatever that the this methyl group will be that the above and why that this one is below, can you tell me? Because in that the stereochemistry I have drawn that whatever that the methyl group that will be present above. Hello. Okay. Yeah. Yeah, if you draw that whatever that structure we have this this bicyclic system you need know this bicyclic system whatever that after that because after the reaction you will get a bicyclic system. Okay. That's whatever that the cyclation in the last cyclation you just ignore. So whatever that after the first attack you will get a bicyclic system. That's all. Generally, Cs will be formed because in radical that the Cs then the class will be has to be formed, but radical as we call them as radical are the much more reactive species. That's why they always give that we call them as kinetically favorable product because their the rate constant is so much faster or that the reaction, and they almost most of the cases they got that because there was sometime also that you will get kinetic favorable for product like when that you have five member ring and six member ring. Suppose that you have five member ring, there's two chances that in some cases you will get five member ring and also that there is possibility of that the six member ring. But in particularly radical cases that you will get five member ring. This is only why because the synthesis of five member that radical ring will be much more faster as compared to that the six member ring. But that we call them as thermodynamically favorable product has to be for, but why not? Because the formation of that the five member ring and that the six member ring, the stability between both of them is no, the stability gap between both five member and six member ring is not that much that the we call them as not that much energy gap. That's why because the energy gap between that the four membering synthesis and six membering is that the gap is very high, but the we call them as energy that between five membering and six membering is not that much gap. That's why in this particular cases that that the five membering is as the synthesis of five membering is much more we call them as faster as compared to six member ring. That's why in this particular cases, five member ring predominantly that's it, form as compared to that six. Yes, yeah, yes. Whatever the radical will be formed, that is tertiary radical will be formed. After that, the first attack. Yes. Six. Oh, then you will get a bicyclic. You see, na? That's from Baldwin rule also that you will get. You don't know that's how that the Baldwin rule and how that the orbital overlap will be possible by that the Baldwin rule or not. That if it is attack in that particular cases, that you will get a what? You will get a secondary that's radical. Along with also that you will get a that a fused bicyclic compound. You think that the fused bicyclic compound is much more stable as compared to that the normal bicyclic compound? That you will get a fused bicyclic compound. You know this one if this bond that will be connected to this carbon, then you will get a fused bicyclic compound. This one is if it is connected to this carbon. Yes or no? Okay. And after that also that it will after proton that it won't after proton that it will after proton, yes, and then you will get your corresponding alkene. You won't get that the addition of tin butyl that the tin radical that yes. Oh, in this particular case, no, that the 5 exotic that's whatever that dig is much more favorable. Do you know why? Because that's when it will attach na, then whatever that's the flexibility of alkyne because they are alkyne are planar. Sorry, that the no that alkyne they are linear. Understand? That's why the attack at that the terminal it's very difficult as compared to our this. Then when you will see that the orbital overlap, then you will see that their we call them as their exo attack is much more favorable. That's why after seeing a lot of things, that Baldwin that's generalize a thing and he gives a rule, and that rule is applicable for most of the law. It's not for all. That's why uh, by seeing or by that observing most of the reaction that's contain the radical, carbanion, and that the carbocation and other kind of cyclization reaction. Baldwin first observe all of these things and he proposed a rule that rule is applicable for most of the cases. It's not for that the all cases. Most of the cases it will be applicable. Based on that only, based on this reactivity, they propose also their orbital overlap, how there the orbital overlap will be there, why that this one is not possible, why other that we call it, another one is possible. That is that the result from that the Baldwin rule. You will get that most description of that the Baldwin rule. It is not given in Clayton books, but maybe because in master I have studied that the orbital overlap also, but I forgot that the book name. If I know, then I will tell you. But there is a book. but that Baldwin group, that how their orbital overlap, everything will be there. There is a book. So that book also you can follow. That if you want to know that the how why that the 6 exotic is not possible, why that one is not possible, so you can check. Yeah. In that the next questions also that we have that's a lot of things that you will see. It's not only one thing that's but okay. No, there is recording or not. No, no. Whatever that I understand, but whatever I am recording, whether it is visible or not, so I am confusing. The slides is visible, I understand, but whatever the video I am recording from that OBS, so I am not confirmed whether slides is visible on that video or not. So I'm checking again if it is. Oh, now it's on. Yeah, now we'll see that we have Python ring with that's contain three chiral center and that's one and three alcohol that will be protected by two TBS group. That's a tot butyl silyl group and one is that benzyl. And that nitrogen also will be protected by Bohr anhydride. Okay. And Bohr group that will be protected. We have that fluoride source and again we have this that dimethoxy one and also the catalytic paratoluene sulfonic acid. After that, the second step, we have hydrogenation. And normal hydrogenation that we have studied in that the reduction. And also that we have oxidation also. And in the last class, maybe we have studied the Wittig reaction and again also hydrogenation. Then what will actually happen? What actually happen in that the first step, we will get in that first step, what will happen actually? That's we have fluoride source and we have yeah, whatever that any kind of silyl that's the protected group, that alcohol or that's whatever, then it will be depleted by that fluoride source. And the particular says that as it is not mentioned that we are giving how much amount of that fluoride, that's why then we'll think that both will be deprotected to their corresponding alcohol. We'll get your corresponding alcohol. Okay. Then that the next step what will happen? That we have okay, from this we have calculated that the PSOH is nothing but yeah that will protect. First, whatever our the catalytic PSOH, yeah, that will react with this one. Then methanol will be removed and you will get an intermediate like this. Okay, and after that, both that both hydroxyl group that will be reacted and you will get we call them as a protection of that the one three diol, 1 2 3 diol. Sometimes also 1 2 diol will be protected by this kind of group and also 1 3 diol will be possible. Yeah. But when it will be 1 2, then in that particular cases they have to be we call them as cis also. And most of the time that cis also be much favorable, but trans also be possible. In this particular case we have trans and also sometimes that the cis also be possible. And after that we have that hydrogen and palladium. Okay, the palladium hydroxide. Uh, uh, Generally that's benzyl group deprotection. Yeah, that can be possible by only the we call them as hydrogenation. The hydrogenation is needed for that the reprotection of OBA. That's why we need the this hydrogenation to deprotect our benzene to the corresponding benzene. We will get our corresponding alcohol. Then we have that TCC. From the TCC, then we will get your corresponding what? That acid or then you will get what? Huh? After PCC, then what will happen? Aldehyde. Then you won't get, you will get your aldehyde. Then after that, then we have wheating. Do you know that's a yeah, transalkene? Yeah, this whether this elide is stabilized elide or how that's we call them unstabilized elide. Cis. Yeah, yeah. In this particular cases, we will get that the Z alkene. Uh, and, and after that also that we have same that we call them hydrogen and palladium. That charcoal, palladium hydroxide and charcoal we have given in ethyl acid at a room temperature, and you will get your corresponding that's that we call them the reduction of that alkene to their corresponding alkane. And you will get your corresponding alkene. Whatever the C12 that will also contain this carbon and this carbon. That's why we mention as a C12. Okay. Do you know that's how to put okay. Then how to put that the Wittig reaction? Do you know? That's whether it will be that the easier to put that the Wittig reaction because that's whatever the Wittig, the unstabilized elites, that's whatever. These are very difficult to synthesize. Yeah. Whatever the stabilized elite, then these are very easy. But whatever that the so whatever that we have we call them as unstabilized elites, first you have to be prepared because from that the phosphonium bromide to their corresponding by using the different kind of bases strong bases that first you have to prepare that woodic salt. That's why these woodic salt are the much more reactive. And these are we call them as through that the we call them air moisture sensitive and that the water sensitive also. So you have to put in positive argon pressure and you have to be in a very careful that if you have there is some leakage or chances of that the air will be there, then your OT will be that quenched by that the air. So that's why the synthesis of that's we call them unstabilized that OT that will be much more important as compared to that the stabilized LED because stabilized LED is much more stable that if you put in the we call them without argon atmosphere also you will get. But stabilized LED that you will get you have to be very careful to put that the that kind of reaction. And also I told somewhere else also that how to put the hydrogenation reaction. That's first you have to put the solvent, then you have to add that solvent first, then only you will purge hydrogen. You can't purge hydrogen before that the solvent. If you purge, then it catches fire. So for that you have to be careful. Um, Yeah. And that the next question we have, you see that the N-butyl, that tin chloride, that and also sodium borohydrate. In the first cases, we have what? That the N-butyl, N-tributyl, tin hydrate, and AIBN. But in this particular cases, we have sodium borohydrate and N-tributyl, sorry, N-butyl tin chlorides and AIBN. And also we have that in the second step, we have sulfuric acid and chromium trioxide. Then what are the products that you will expect? No, what's first? What will happen? That the whatever that the reagent condition first one. What is it? Why that we have given that sodium borohydrate? Huh? Really? The first step? No, no, no. That's N-butyl tin hydrate that will react with our carbon bromide. Then it will generate radical. Only tin butyl tin chloride it won't generate a radical. That's whatever that's the radical that will be generated first by AIBN and after that whatever our sodium borohydride and 10 that the tin triacid tributyl chloride that both will react and it will gives that the tin tributyl hydrate. After that, the reaction between sodium borohydride and tin chloride, then you will get your corresponding tin. That tin hydrate, whatever that. After that, only from AIBN, then you will get your corresponding that tin tributyl radicals. Okay, the reaction between sodium borohydride and tin chloride, the tributyl, you will get your corresponding tin butyl. That we call it. Not butyl, it's tributyl hydrate. Okay, so only that's the we call them as reactivity of that in the particular cases. This is sodium borohydride is nothing but for that the generation of this hydrate, the tin hydrate. After that, you will get your corresponding tin radical. You won't get if you don't add sodium borohydride, then you won't get that radical, that the tin radical. You will only get this radical. Okay. Mm. Then after that, what will happen? Then it will generate a yeah radical. Whatever the radical it reacts through the homolytic cleavage, then you will get it. And in this particular cases, we have two different type of that addition. That this like 5 exotic and 6 exotic. Always that the 5 exotic is favorable as compared to their our 6 endotric. Okay, always the 5 exotic, 6 endotric that favorable as compared to their the over that the 6 endotric, and also that's 5 endodic also favorable. That's over we call them as 5 like 5 exotic. That's when also it is triple bond also in this particular cases also you will get that the 5 exotic that favorable over 5 exo sorry endo d. In this particular case, you will get your corresponding that why we will get that the cis one. Then you will see from this transition state. You will see that so whatever the transition state, you will get so whatever your third butyl group present, and after that, the after addition, then you will see this methyl group that will present above, but this one that will present below. You will see in transition state. You will see whatever that, whatever after that the attack, then you will get your methyl group up after that the bond formation, and whatever you taught with it, that will be below. And that you can put your that's whatever OA2 group also that below. Yes, I'm not missing, but you can put your OA2 group your corresponding the OA2 group to their corresponding that in below positions also. And after that we have that tin hydrate, that tin the tin hydrate, and it will after that proton, and you will get your corresponding that we call them as the cyclase 5-member cyclase product about the 6-member ring. And the stereochemistry that's from this transition state, then we have to always decide. Okay. And after that, what will happen? As we have sulfuric acid and chromium trioxide. Uh, Yeah. From sulfuric acid, it will hydrolyze, and after that chromium trioxide, you will get your corresponding that lactose. Yeah, thing because this oxidation, the reaction you have already studied in that past 3 to 4 lecture course. Maybe that is content of a 4 lecture. Maybe. Because in radical cyclization, that's you have to be very careful that there's a lot of that variety of cyclization or the lot of variety of reactive center will be there. So first you have to decide at which center the reaction will happen. And decide is that the most important things. Okay. In this, that the next question that we have also that same that's if I'm not wrong, this is a question from that CSR net also. Okay, I'm not wrong. Yeah, gate. I don't think so. And that's we have the tin butyl, the tin hydrate and AIBA, benzene and reflux. Then what will happen? Huh, huh. And after that, what will happen? So we'll get our corresponding radical. That's the first step. Okay, then after that, what will happen? We'll get our corresponding radical. That's it's okay. Then it will attack to cyclopropane. Is it possible? Okay. Huh. Yeah, that will open. Yeah, that's the way. But first, what actually happens that it will attack to our alkene, whatever the alkene. Generally, radical as uh, whatever the radical, these are much very active towards that you call them a cyclopropyl ring and alkene, alkyne. Much more reactive towards alkene, alkyne, and cyclopropyl rings also. But in this particular cases, we have alkene and cyclopropylic, and alkene attack will be that the much more easier as compared to that cyclopropylic. But that cyclopropyl ring also after that attack, then it will be one. What we will see first, the cyclation will be happen that you will get your corresponding cyclation and radical here, and after that what will happen? We will see from this radical, then this cyclopropyl ring will break. So whatever the ring will be through the homolytic cleavage, and you will get your corresponding alkene, and whatever the radical, we call them carboxylate. The alpha carboxylate radical will get that this one. After that, the ring cleavage of the cyclopropyl. Then in that the whole reaction, that's because we are discussing what charge the laptops. Charge. Oh, what? Oh, then okay, maybe in that question or in that option there is something will be wrong. I don't know. The whatever the option, maybe it's something wrong. Okay. Question, it's not like that. Like maybe that instead of the oxygen, whatever that the oxygen we have, maybe when I have made that slides, then I did some mistake also. That instead of in this particular case we have oxygen also. That option is correct. So maybe there will be that the oxygen here. I don't know. But if there is oxygen, then this option is that correct. If there is no oxygen, then that whatever that option we have, then we have to put the carbon in that the options. Okay. Yeah. Yeah. I will change that the slides when I will upload the slides. Okay. Hmm. After that, then it will abstract that proton from that this tin butyl hydrate, and you will get your corresponding that cyclic product, the tricyclic product. You see that we have only benzene ring, but after that the radical formation through only that you will get a tricyclic product. That is the fused tricyclic product from the radical intermediate only. But if it is a carbanion or the other kind of the intermediate, then you won't expect that kind of that cyclage or the other that kind of reaction is not possible through the other kind of, you call them as intermediate. But from radical, that you will always expect that the different, the unexpected kind of product also. That in that the upcoming slide we'll see. Uh, in this cases, I will see some that problem about that silicon based reagent. There. Then what will happen? That we have potassium hydride is a what? Yeah, it's a strong base. Why it's a strong base? These are, yeah, these are the yeah, these are the, but whatever that the hydrate, the hydrate ion, these are much more stable. Whatever the hydrate. Okay, that's what hydrate. What is the size of hydrate ion? You know the size of hydrate ion. Whatever that the size of that hydrogen and hydrogen. What is that the difference between that the hydrogen size and hydrate ion size? There is a big gap. That the size gap between the hydrate and hydrate ion. Hydrate ion. The size between, maybe you know about this or not, I don't know, but in organic chemistry, that is, when you will see that is the comparison about there's some carbanion, sorry, but anion, that's the size of that the anion, that hydrate anion will are that the much more, maybe it is equivalent to that the two second row or that the third row that carbanion. So we'll see. But these are actually generally strong bases. Then what will happen in this particular case? You have option also, but this question you can predict, I think. The answer you can predict, if I'm not wrong. Actually, what will happen? I don't know about option. Whatever the option, yeah. Okay, that's I will check. Cyclopropane intermediate? Also, cyclopropane that whatever the potassium hydrate, then it will after the proton from where? OH, then from which OH? Mm, oh, nah. Whatever. That's whether the hydroxyl group that will be OH or that's gas. That's which hydroxy group? That this top one, this one or this one? This one. Yeah, this one. Okay. This is only why. No, that it will after. It will after both one. Okay. But the reaction, whatever will be happen, that it will after both. It is possible also that it can after both. Whatever that the reaction, it will be happen. Then, as if you see that the cyclohexane ring in that, and if you put that all the substituted, then you will see what is that the actual region that the which hydroxy group will react with our silicon. Maybe you will know that the Peterson olefins reaction. You know that's what is Peterson olefins reaction. Yes. But in this particular case, that we have two different kind of hydroxy group. Then which one it will be for? Then which one that will be present as a diaxial. Now we call them as from same sides only because in the opposite side, the donation of this that the negative charge to their corresponding silica, that it is not possible. That's where it will be in that the same size. That the in that the cis position. General cis position, it can easily donate from that the same size only. It can easily donate to their corresponding silicon, and it will form a that the four member ring. That's whatever that the and four member silicon oxygen bond will be formed. And after that cleavage of that bond, you will get your corresponding alkene. When it comes to cycling, then you will get your corresponding always that the if it is 6, 7 or 5, 4 ring in that multiplication, you will get a Z alkane. Thus we will get our corresponding allylic alcohol. And also this allylic alcohol also that you can oxidize to their corresponding that the epoxides also that cyclopropanation whatever that you want to do through that alcohol also then you can use to their further functionalization of the group. We have that MCPB that metachloroperbenzenic acid. That's why it will selectively, that's whatever the epoxidation that will be formed from the same sides of our hydroxy group through because of our hydrogen bonding of that the MCPBA in the transition state with our allylic alcohol. Yes or no? Suppose that if you have instead of OH, that if you have OR group, that O methyl group or the O something group, then you will get your epoxide from we call them as that the other phases like from that the OH phases then you will get your corresponding epoxide because of that hydroxy group then you will get your the epoxidation from that the same phases of your hydroxy group because of hydrogen bonding and that transition state we call them as a butterfly transition state. Do you know that what is that the transition state through that MCPB that will reacts with our alkene? Yeah, do you know the transition state? The selectivity you know, you don't know. when there is a that the hydroxy group, that in that particular cases you will get your corresponding the defoxylation from that the same side, from the same side, because of that the hydrogen bonding. So whatever the hydrogen bonding with our MCPBA, that's what we will get. Okay. Yes, yes. In this particular case, huh, no. That's I'm asking. That's suppose that if you have whatever that the OH group, suppose that you have that the OME group, then what will actually happen? That's not. Suppose instead of that the OME, let's say we have OL. Suppose that you have instead of OL that you have OME. Then what is that the product you will expect? What are the epoxidation that you will get from the other sides? Because in that particular case you don't have any kind of that hydrogen bond. Because in this particular case, yes, whatever that the epoxide will get here only, but the stereochemistry of epoxide will be different. Okay, yeah. Ah, because of that stereochemistry, because in that particular cases we don't have that hydrogen bonding, na. Okay. Now that we have, as we have teen also, but because we have not studied yet the palladium one, but still that I have attaching that some palladium also, and iodination first the iodine pyridine and the palladium PPS3, and along with that the tin butyl that we have, that is salt, and along with that the sodium borohydride and sodium trichloride, that the hexachloride, the trichloride and 7 the H2O that you have studied. And what will be the expected product in this particular case? So we don't have any kind of stereochemistry, nothing. But first we have to predict that the which one is the product. Actually, what will happen in that the first step? See, then what will actually happen? So whatever the alkene, and it will react to our okay, and after that, the elimination of iodine minus, then it will again attack. Then you will get your corresponding that the trans, that's whatever the trans diiodine that you will get. Is you won't get the cis one. I am not here mentioning the stereochemistry, but you will get that trans. Yeah. After that, what will happen? Yes. No. First we'll see. So yes, what will happen actually? That not one. The iodine and hydrogen who will be replaced. But which iodine will be replaced? Because this hydrogen, that's whatever this hydrogen, that will be that the much more acidic as compared to this hydrogen. That's why we will get our corresponding that iodate. We call it the carbon sp2 iodate. That in that whole process, that what actually happened? That's whatever that the iodine that will be connect at that the alpha position without changing up the cyclohexadiene, sorry, that the cyclohexanone ring. Okay. And why that we have synthesis this? Because that after that we have palladium. This palladium and tin, that source. Then after that what will happen? Still a coupling. Okay. still we will get the then corresponding that alkene, whatever that the alkene, that's whatever the still coupling that will be connected to our that the iodide one through the still. This is a coupling reaction. The mechanism so we'll discuss later. And after that we have sodium borohydrate and the sodium trichloride and that seven to water. In this particular cases, that it will reduce to their corresponding allyl alcohol. Okay, because in that particular case we have alpha beta unsaturated ketone also, but because of that the selenium trichloride, that it will only reduce our keto to their corresponding alcohol. That's whatever in this particular case we have allylic alcohol. This one. And the general mechanism for that the still a reaction, that's whatever that palladium zero source after that, that it reacts with any kinds of that this one is R1 and this one X is nothing but iodine. First it will undergo the oxidative addition, and along with that the transmetallation through that the tin ones, and after that the reduction we call them that the reductive elimination will be happen, and you will get your corresponding that coupling product. Okay, so three mechanisms there. The first one is that the oxidative addition with that's whatever that the RL halide, and after that the transmetallation, that's if you have any that the tin and that any kinds of the instead of tin also, that if you have any other kind of that metal also, then we call them as a different name reaction. But for this we call them as Stille coupling. That's Stille coupling reactions. So it is transmetallation and along with that the reductive elimination, and you will get your corresponding coupling product. This is that the general mechanism. But the more details I would see in palladium, and how that stereochemistry also, that we'll see that sometime when they will that the transmetallation will be happen, and or when that the coupling product will be formed, then whether the stereochemistry of Z or E, that the which kind of stereochemistry of Z or E will be formed. That one also that we will see in that the palladium based reagent. Okay. And that, yeah, yeah. This one is our the next question. You will see, and we'll get the maybe in this particular cases. So this will get two or three. You know what will happen? Yeah, for past stage that's okay. After that, what will happen? Yeah. Then you will get a alpha cyclic helical. After that, this whether this helical will react with which one? The, it reacts with which double bond? This one or this one? The actual product actually we are seeing. I will show you. This double bond. Yeah, you will get here. That the how many members that will get? The number of that whatever that the ring will form. Whatever the ring will form. The ring, the cyclic lattice will form. That's okay. Uh, the ring size is nothing but 1, 2, 3, 4. The carbon it will contain 1, 2, 3, 4, 5, 6, 7, 8. Eight members. Generally, what happens, the synthesis of that high memory, that's the it will be very difficult sometimes. Most of the time that we won't get that high memory because of their orbital overlap and their thermodynamically there's the favorability. So to synthesize that any kind of that high memory, then you will get a very good journal. That's in the organosynthesis that you can publish a paper that if you synthesize that any kind of higher memory. High memory is much more important. Okay. These are for the research one, but that's when you go to the research one, then you will know all these things. So Ah, in this, that the next question that we have, that but in this particular case, you will get maybe that the variety kind of product, and also that all that product that will get for them as a different kind of yield also. If you want to check, and what will actually happen, then we will get our corresponding in the first cases that the radical will be for, but after that what will happen? The cyclization to that the alpha beta side. Generally, that's we have this alkene and the another kind of alkene, but this alkene is much more reactive as compared to our keto group, and it will attack to that position. After that, whatever that the acyl is radical, then it will react with our so it can after the proton also, and you will get your corresponding that this product, and also that it can that undergoes a that the 6 endo and also that the 5 exoteric that it will react. And after that, whatever the tertiary radical will be formed, then it will undergoes a that the 5 exoteric of the this radical, and you will get a that's the fuse that the tricyclic compound. And after that, the hydrogen after some, then you will get a tricyclic product with that the 33% A. Whatever that you will get three different kind of product. The first one is that after first attack, then you will get a particular that the hydrogen single attack, and you will get a corresponding that the alpha acyl radical, and that radical that will after the proton, and you will get your corresponding that whatever that the only the cyclopentane ring with substitution you will get as a 23%. And after that, what will happen? That some amount of this kind of radical, then it will react with uh, to that the cyclism, that the whole cyclism. That in this particular cases, you will get a 6. You will see in the particular because of that the stability of that the tertiary radicals, and there is that the whatever that the attack that will be happen from primary center. That's why it will be possible to get a 6 member ring. That's why I told you that the Baldi rule that will be not applicable. That's always for our the radical cyclism. In this particular kind of cases, that's when you have that the generation of tertiary radical, and also that's when your attack will be happen from that the primary radicals. That this one is not primary. This is secondary. Okay, this one. Then you will get your corresponding that the 6 member is also be possible as compared to the other 5 member ring. And after that, the hydrogen accretion also you will get your corresponding that the 44%. Why? That you will get as a 44% because this is radical is much more stable age. That's why it always that the always tends to be the major product to the corresponding product. But there is some radical also they undergoes that it reacts with our alkene through that the cyclism, and after that also that you will get a that hydrogen abstraction also, and we'll get our that the 1 2 3 that the tricyclic compound with that the fuse ring, that even with that the fuse ring is also possible through that the radical cyclism. That's why in radical chemistry that you will get that the very different kind of product, that the very different kinds of that the product with a different E. That's where the side reaction that if you want only one product, then it will be very difficult to control that the radical reaction. That's why people they have used some kinds of metal, some kinds of particular directing group, or there are some kinds of particular reactive center to get selectively one product over that other product. Okay, that is the particular. So you will see that the maybe that you will get that the 3 4 products and the 5 product also that you can it is possible to get sometimes it is possible. That's where radical the intermediate and the much more reactive settings. And in that the next questions, yeah, yeah. Today we don't have much more slides. Yeah, this is our I think if I'm not wrong, this is my last slides. Okay. Hmm. Then what will happen? That we will see that some problem related about allyl silane also. That you will see this one is allyl silane. and we have that the N, that the tributyl, that N, that butyl, that the ammonium fluorides along with DMF and HMP. Do you know what is HMP? Yeah. Then in this particular cases, what will actually happen? Yes, we have fluoride source. Then what? Yeah, not reflect, that it will only deprotect, that the fluorine and silicon bond, that will be much more stronger bond, that's why it will react with that silicon, that the silicon vacant the orbital, whatever that the vacant orbital, vacant p orbital, that fluoride ion, whatever that anion, yeah, that will be donated to their we call them as vacant orbital, and we will get our corresponding silicon and fluorine strong bond. Why this is only strong bond? Because after the bond formation also, eh, there is another we call them as the vacant orbital of p orbital, and uh, and whatever that the lone pair that will be present on that fluoride, it can again donated to their that their vacant orbital. That's why silicon fluorine bond are the much more stronger bond. That's why this we call them as attack, that we call them sometimes also we call them as deprotection of silyl group through the fluoride. This is the only reason that we call it can deprotect their silyl groups very easily. That is the only why that silicon fluorine bond will be much more stable. This is only because that whatever after that the bond formation also, as whatever the lone pair that will be present on fluorine, and it can don't even for that oxygen also that is possible, because oxygen lone pair also that it can donate it to their vacant orbital of that the silicon. That's why these bonds are the much more stable bonds. The silicon fluorine silicon fluorides, that the fluorine and silicon oxygen bond, these are much more stable, we call them as a stable bond. That's why this reaction is as we call them as a faster reaction also. And we put this kind of reaction in the 0 degree Celsius, like sometimes to control their reactivity. In this particular case, that's whatever the fluoride is there, it will deprotate. After that, the deprotate, what will happen? That's whatever the negative charge. Yeah, it will comes to here, then you will get a carbanion. That carbanion is stabilized by our alkene. That we call them as a allyl carbanion. Okay, then after that, what will happen? Can you guess? Then what will happen? What? TMF. You think? Yeah, TMF. These are the solvent only. Solvent. You get a cyclase ring. How that the cyclic ring will work? So whatever that this nucleophile, then it will attack to the alpha beta unsaturated ketone, and you will get your normal that that is we call them as addition, and that we call them as one for addition and alpha beta unsaturated ketone or the carbonyl compounds to their corresponding uh, you will get your corresponding that the addition product, that the one for addition, that instead of O1 to addition, because this carbonyl is that we call them soft also, and this carbon center is that the soft electrophile, and also as in the particular case if it is attacked to that this carbonyl also, then it will be not possible, because if it is attacked then you will get a very straight ring, and that straight ring is also not possible to exist. That's why that kind of ring won't be formed. And in the neck reactions also, that's we have allyl silane, but instead of the first cases, in that second cases we have Lewis acid, that the diethyl aluminum chloride. Yes. Yes. First you think then what will happen actually. How that the reactivity will happen. So whatever that is one. Yeah, what we were saying is that this carbonyl group that will be activated by our Lewis acid. Then that the Lewis acids. Okay, and whatever the allyl silane, they are sometimes behave as a nucleophiles. This is nucleophiles. Whatever this one, this alkene, and it will react to that the 1,6 positions also. In that 1,6 position, and you will get a after that the cyclation product, the bicyclic product, you will get a carbocation here. You will see this carbocation you will get because this oxygen, that's whatever this carbon group that will be activated by our Lewis acid, and also that's whatever our alkene, yeah, it will react at the 1,6 position. Why not the 4 position? Because that the 4 position is much sterically hindered. That's why it will attack to the other 6 position, and you will get a 7 member ring and also carbocation. After that, what will happen? Yeah, yeah, whatever the silai group, yeah, it will be removed and you will get your corresponding that double bond. And after that, as whatever it will converted to through that, when this it is converted to their corresponding after that do workup only after when you will do we call them perform workup, then you will get your corresponding that the alpha beta unsaturated ketone through that the isomerization of this double bond, because after that the workup also you will get it, that the more stable alkene, whatever the alpha beta unsaturated ketone alkene you will get as a more stable alkene. Yes or no? Yeah. After that, the workup only. Okay. In the whole reaction, you will get up to here. When you will do workup, then you will get this product. Yeah. This is my last, because they are the last slides for today. Okay. Today we have that only because there was 9 slides. That's all content about that either silane or that tin best reagent. How the reactivity, particularly for the radical reaction, how it will, and also we'll see some that stele coupling also. Let us see. If you have any doubts, then you can ask, and also that if you have any problem related about the assignment also, because the last time someone, maybe you and someone, he told about the assignment. Okay, I forgot that the question number. That you told whatever that you or someone else he told about. Okay, yeah. Yes, because I forgot that question number, so that's why whatever the question I remember at that time. And I went to the lab and I told my senior. But after some day I forgot. So I don't know. Because and that whatever that discussion of that one also it is not recorded also. So I'm not but still if you have any problem related about that questions, that's whatever the question and maybe some question is wrong also sometimes, and also they are often also wrong. So that's if you have any problem then you can ask in that the here also that, or you can mail to them also, the NPTEL and also them, that you can, it's not a problem. And still, if you have any doubt, then you can, if you have any doubts, okay. Okay, then you can leave. Okay. Yes. Oh, okay, thank you. Yeah, next week also we have class. Okay. Thank you.